All right, afternoon everyone. We'll be starting in about 1 to 2 minutes time. All right. So the three lectures for today, as you can see in the live stream description, are going to be basically the signals and systems lecture, the basic signal operations lecture, and then the special signals lecture. We'll be doing each one of these in turn as we keep on going along. Now, you weren't present yesterday, we didn't get a chance to watch the video lecture from yesterday. One of the most important key points is that if you have any questions, feel free to type them in the chat. And after I finish discussing a particular slide, I will answer these questions accordingly. If you do not want to publicly ask any questions, you are free to email me questions afterwards, or you can try to get in contact with me in some other form or fashion, but most likely email is going to be the best way to communicate with me if you really need to talk to me privately. All right, so our first lecture today is basically what is going to be our signals and systems course and the terminology that we're going to be using in particular. So the following model here is what we're going to be using for any typical system that we're going to be encountering throughout this course. And the model here basically describes three things, which is going to be our inputs, which will be our input signals, our system here, which will process these input signals in some form or fashion, and our output signals here, which will be the result of this processing of the input signal here via the system to obtain our required output signal here. So any input signals in particular could be voltage, current, force, pressure, or any sort of thing that was going to be supplied to our system. And the output signals could also be similar in nature or an entirely different signal. So we can have an input voltage but producing an output pressure as accordingly. And these will be produced by the system as a response to the input signals, where the system does the processing on the input signal. There's also a third category of signals known as internal signals, which is produced within the system. And this typically occurs when you're transferring information from one system component to another. So for instance, let's say we had a two-stage filter, which acts as our system. The output of the first filter will be an internal signal acting as the input to our second filter. And then the overall result will be our output signal coming out of the entire system itself. Another form of internal signals within your system can also be what we refer to as electronic noise or unwanted signals that interfere with the processing of our signals within our systems. So in general, signals are basically some sort of function with respect to time, frequency, or some other parameter that basically represents and carries our required information. So in particular, our electrical signals will be voltages and currents with respect to time or frequency. Acoustic signals, which will also be audio or speech signals, which are literally air pressure variations, but can also be respect to time and frequency. Video signals, which are also respect to time and frequency as well. And biological signals, which may be respect to space in particular, or a certain type of sequence. Now, note that from my explanations here, all of these signals tend to be with respect to some form of base units. In this case, it could be time, which is seconds. It could be frequency, which is hertz. Or it could be speech, which is just basically the positioning of your signals in themselves. So all of these signals in particular are always with respect to some base units. The outputs of them, for example, voltages and currents, voltages will be in volts, and currents will be in amperes accordingly, which is typically going to be our y-axis value if we decide to plot these signals. And our x-axis value in these cases can be a time with respect to time or with respect to frequency. An internal signal, yes, can be something referred to as heat, where the heat signal can be a byproduct of the system itself, and it may actually interfere with the processing of certain signals within the system itself. So yes, an internal signal can actually be heat. So, like I said in the previous slide, the signals are basically functions of one or more independent variables, and they don't always have to be categorized by one independent variable. So, you may have a signal that can represent distance, time, and force all together, or you may also have a signal that just represents time and distance. So, it's not always limited to just one independent variable. It can be multiple independent variables for these signals. However, for our purposes, we'll be focusing on only one independent variable per signal as we go throughout the entire course. We will not be looking at two-dimensional or third-dimensional signals or any higher dimensional signals as such. We are only focusing on one-dimensional signals in this course. All the electrical signals that we're going to be focused on here will typically be a function of time unless we transfer it into another domain, where you will see later on throughout the course, it will end up being a function of frequency. Now, the purpose of doing the analysis of signals and systems basically helps us observe signal characteristics and the performance of a system in particular. So the characteristics of a signal can be the variation of the signal, or if the signal repeats itself after a certain amount of cycles, or if there's a particular section of the signal that you are interested in and you don't care about the rest of the signal. Those characteristics are actually what determines the importance of the properties of the signal itself. And our system performance can be characterized in many ways. On the slide here, we basically talk about the gain of the system, which can basically be for your filter designs, and your frequency response as well, which gives us an indicator of how well your filters perform. If it's going to be a low-pass filter, a high-pass filter, or a band-pass filter. Do you actually have the cutoffs at the correct frequencies? What is going to be your roll-off at these frequencies, and so forth. So system performance is also characterized there by observing how the system processes the input signals to produce our desired output signals. Another indication of system performance can also be accuracy and precision as such, which tends to be measured in percentage. So for all purposes, we'll be using mathematical models for all signals and systems. And an example here can be seen as this current signal here with respect to time. Now, in particular, we can observe here that our signal here has a frequency, it has a phase shift here as well, and it has an amplitude. So these three y-axis properties, you can basically say, sorry, not y-axis, these three properties represent our y-axis and our x-axis properties if we decide to plot the signal on a graph. So the frequency of this current here, as we can see from our equation, we have 40t. But as we know, frequency is equal to 1 divided by t. So we just plug that into our equation and we can obtain the frequency of this current here accordingly. We also know what's the maximum amplitude here, as given by this value. And then we also know what's the phase shift here, as given by this value here. So the equation that describes the residential voltage supply from one of your output plugs tends to be that, let's say we're using 120 volts RMS. The frequency there is basically 60 Hz, so we'll be doing 1 divided by 60. And any relevant phase shift would be there accordingly as of such. So if we need to write this equation, it typically would be something like, let's say, y of t is equal to 120, 1 divided by 60t, minus some phase here accordingly. The 1 on 60 here is basically frequency is in relation to periodic time and so forth, in order to obtain your equations here accordingly. So this typically tends to be a relationship between any visual aids and mathematics. And for some reason the figure hasn't shown up here, but I will show it in a few later slides, which we can have some visual aids showing this in particular. But we can also model any systems using transforms. And in particular, you've been exposed to one transform here, which is known as the Laplace transform. And we also see that when we obtain our Laplace equations, we also refer to this as a transfer function, which maps the output signals to our input signals accordingly. Or in a short version, it's going to be the output divided by the input. Here we go. There, it's already figured itself. Right. So basically, we know from our electrical analysis that our equation here representing our electrical circuit can be represented as a differential equation accordingly. So the differential equation here can be obtained from actually watching this physical visual aid that describes our electrical circuit. And then it's also possible to obtain our Laplace equations here from our differential equations as of such to model our actual system itself. So as such, we can have a y of s representing the output here and an x of s here representing our inputs. Other visual representations actually exist within our course. And in particular, one visual representation that we will be using later on is going to be our block diagrams. As of such, our output here is y of s, and our input here is x of s. And this entire system here is how the x of s signal is going to be processed to produce our y of s signal here accordingly. And the block diagram is going to be explained in later lectures as to how we actually obtain our YFS signal and how we actually obtain our transfer function mapping our YFS signal to our XFS signal. Now in this course, we're going to be focusing on two categories of signals. In particular, we'll be looking at continuous time signals, and then way later on in the course, we'll be looking at discrete time signals. For the majority of the course, we'll be focusing on continuous time signals until the last 3 lectures, which is going to be heavily focused on discrete time signals. So our continuous time signal tends always to be a function of time, unless we do some transform in it to get into a function of frequency, as of course accordingly. And for any instance of time, there's always going to be a resultant value. So we can say time is equal to 0.001, and we'll obtain a y value for this time in particular because of the mathematical nature of the signal. So continuous time signals will also be processed by a continuous time system. And as of such, in doing this processing, we tend to focus on only continuous time transforms for these signals. So for instance, the Laplace transform is used for only continuous time signals. If we had a discretized time signal, we would need a totally different transform, which we'll be seeing later on throughout the entire course. A good analogy of what a continuous time signal is that any analog signal that exists, or most of the signals you deal with in the physical world that is not digital in nature, always tends to be continuous time signals. So what happens if we only observe the continuous time signals at particular instances of time, where these instances tend to be evenly spaced? What happens here is that in observing instances of the continuous time signal with a particular time interval, or what we also refer to as our sampling time, this is actually the process for transforming a continuous time signal into a discretized time signal. And instead of it being x of t, where t is common, the discretized time signal is represented by x n of t here in square brackets, where n here represents the instance at which you observe the signal, and capital T represents our time interval or sampling time. So for instance, if we wanted to know what is going to be x of naught for this signal here, we'll be looking at the first instance, being our 0th instance here, to observe what the value is. And then x of 1 will be this instance here, x of 2, x of 3, x of 4, x of 5, and so forth. So in order to obtain a discretized time signal from a continuous time signal, we basically sample the signal using a set time interval. And at each time instance of this time interval, we obtain the instantaneous value for that particular time. So let's say our periodic time space in here, capital T was like every 1 second, and the capital and common N here represents our instances at which we sample at. At n equals 0, we will have this instantaneous value here from our continuous time signal. At n equals 1, we have our instantaneous time value here, and so forth as we keep on going. So n here, common N, represents the instance at which you are at, or the sample at which you are at. Capital T here represents our time interval or sampling time, meaning the time spacing between 2 successive instances or 2 successive samples. So in particular, whereas our continuous time signal would have been x of common t, or discretized time signal is going to be x of common n. So I'll have to illustrate on the graph to explain it a little bit better. So axis here is with respect to n. And we have instances of n here representing our samples. So whereas in continuous time, this would have been x of t, in discretized time, this is going to be x of n. Capital T here represents our sampling time, or this interval time accordingly. So let's say if t was equal to 0.01 seconds, where we have our spacing here between here and here, that space in there is going to be capital T, which is our sample time. This instance here, which we measure, is going to be n equals 0. Oops. So this, hold on. So this instance here, where we take this sample, is going to be n equals 0. But then for the next successive sample here, that's going to be n equal 1. So capital T is held constant, meaning this is our sampling time, but for every instance of our sampling time, it's represented by common n. So yes, the question here we have is, would n be the particular sample number, which is, yes, that is true, that's the particular sample number, and t would be the inverse of our sample rate, meaning t is our sampling time, 1 on t is going to be our sampling rate. So yes. Alright, are there any further questions regarding this slide in particular? Alright, okay, so we're continuing at this point. So, some nice examples of discretized time signals would basically be any sort of digital signal you can encounter. So, DNA-based sequences, which are basically a digital form of the actual DNA from your body or from any sort of tissue, is actually a discretized time signal because it actually operates on samples accordingly. And population sampling is also a discretized time signal as such. It is also possible, because discretized time signals are digital in nature, that you can actually generate or create your own discretized time signals. So in particular, it can be stock market quotes, it can be your digital images that you take with your cameras, it can be MP3 music files and so forth. So to give you a good idea, for digital images, you tend to see, like, for your cameras, your camera is always rated in megapixels. And the reason for the rating of the megapixels is to indicate how much data can actually be captured and stored on your physical, from your physical captured device to an actual representation as an image. So for instance, let's say for a 2 megapixel image, the 2 megapixel actually represents how many samples you take, which is basically 2 million pixels. But a 10 megapixel camera is going to be 10 million pixels, meaning that there's an increased resolution because there's more samples that are being taken. Music in particular, if you're talking about like analog music, that tends to be continuous time. But digital music is actually when you sample this analog music itself. So like MP3 files in particular, and if you have WMA files or FLAC files and so forth, any files that you actually have on your computer that you listen to, which represents our music, those are actually sample versions of the analog music that you actually have. And if you have ever noticed, you'll notice like if you're dealing with an MP3 file, you always tend to see that there's a sampling rate being like, maybe like 192k bps or 320k bps, which is basically kilobits per second. That's the rate, the sampling rate at which how many samples are taken from that actual analog music file or that analog music that you actually listen to. So, for instance, 128 kilobits per second tends to be your general bitrate that you get from MP3 files, which tends to be an okay quality. And as you go up in quality, like 192 kilobits per second, 320 kilobits per second, you get higher quality music. However, the trade-off is as you take more samples, you tend to take more memory. So a 128 kilobit per second MP3 file might be about 3 megabytes. But when you go like in the realm of 320 kilobits per second, you tend to see those files going up to like 8 or 9 megabytes accordingly and so forth. So digital music in particular will be a discretized time signal because it is a sample version of the actual analog music. And later on, yes, we will get onto something we refer to as the ideal sampling frequency, which is going to be, or the ideal sampling rate, which is going to be 2 times the highest frequency of those sound waves, or the particular highest frequency within your original waveform. But we'll get to that eventually in later lectures and so forth. So why do we actually want to sample continuous time signals to obtain discretized time signals? Well, the main reason for this is that any digital signal that you have or any discretized time signal, it makes the processing a lot easier to do using any computers or any discrete signal processors and so forth. And in some cases where you tend to have asynchronous signals or aperiodic signals where the period is not known, this is actually the only way you can observe the nature of a continuous time signal. So discretizing a signal means that once you have it in a digital form, it's very easy to manipulate because it's just basically going to be a sequence of programmatic numbers, and you can just manipulate those numbers accordingly in any form of sort of transform on your computer or using a processor and so forth. So a discrete time signal or a discretized time signal will only operate on discretized time signals or discretized time systems, and a discretized time system will only produce discretized time signals as well. Oh, one correction to the slide as I'm here. This is not supposed to be signal. This is supposed to be system. The discretized time system will operate only on discretized time signals and produce discretized time signals. And the process that we use to obtain a discretized time signal from a continuous time signal is referred to as sampling. The analog circuit can actually be observed here accordingly, where this switch here closes at every t seconds being our sampling time, and we obtain an instantaneous value of whatever our x of t signal is here to obtain our x of NT signal here in discretized time form. And in particular, we'll be talking about sampling in a lecture later on, most likely next week. Alright, so that brings us to the end of our first lecture. And basically, from what we saw, is that we're going to be dealing with two types of signals, which is going to be continuous time signals and discretized time signals. For the majority of this course, we'll be focusing on continuous time signals and continuous time systems until we hit the last 3 lectures of the entire course, in which we'll tend to focus on more on the discretized time signals and discretized time systems. Are there any questions regarding the material of the first lecture at this point in time? Alright, if there are no questions, we're moving on to the second lecture. Okay, so our second lecture here is basically going to be focusing on basic signal operations that you're going to be using throughout the entire course itself. And these signal operations are actually going to be quite important as to how you can actually manipulate signals accurately and how to represent these manipulations mathematically as well. In particular, the material in this lecture tends to focus on one particular question that either may come on your midterm or on your final exam. If it comes on your final exam, it tends to be 20 marks out of the 100 marks. If it comes on your midterm, it tends to be somewhere rated between 8 to 10% out of the 20% of your midterm itself. So, there are various ways to manipulate your signals accordingly, but the 3 that we're going to be looking at in particular are going to be time scaling, excuse me, alright, sorry about that. So, the 3 particular manipulations that we're going to be looking at is what I refer to as time scaling, time reversal, and time shifting. And we will be looking at each one of these in turn throughout this lecture. So we're focusing on time scaling first. And what this basically does is that it allows us to expand or compress our signal along the time axis. Someone may ask, well, what's the purpose of this? Why would we want to do this? So let's consider the following example here. So we have our f of t signal here, represented by our mathematical equation, and if we decide to plot it, we get this nice curve here accordingly for f of t signal. So instead of having f of t, let's say now that we actually replace this with f of 2t. And if we decide to plot f of 2t along with f of t here, we can see that basically our signal has shrunk. The blue line here represents the original f of t signal, and our green line here represents our new f of 2t signal here accordingly. So Instead of being f of t, and now that we have actually done f of 2t, our signal here compresses because it occupies less space on the time axis. So instead of f of 2t, let's say we decide to plot f of 0.5t. And let's plot this along with the previous two signals. What you see here is that our blue line here still represents our f of t signal. Our green line here represents our f of 2c signal, where you can actually see it's compressed. But our f of 0.5t signal here actually is way bigger with respect to time. So in this case, it actually expands. So in concluding, for actually observing what happens when we start manipulating the factor in front of t here, if this factor is represented as f of bt, if b is more than 1, the signal itself is going to compress. If b here is less than 1, the signal is going to expand accordingly. And the importance of compression and expansion of a signal comes with if you intend to observe particular properties of the signal itself. So I'll give you a physical example. Let's say for an audio signal. The expansion and compression of an audio signal determines actually the playback speed of this audio itself. So in particular, when you say you want to listen to an audio at half of its usual speed, that means you're actually doing f of 0.5t of that audio signal. So you expand the signal accordingly, or if it appeared as if it's only playing at half of the original speed. If you wanted to listen to it at twice the original speed, it's going to be f of 2t accordingly, meaning that you compress the signal so it occupies less time accordingly. In particular, where we say for f of 0.5t, this basically represents, instead of f of t here, the 0.5 means is now twice that of the original time for the entire signal because it expands accordingly. So let's say we assign an arbitrary value to t. Let's say the original time was 30 seconds. When you go to f of 0.5t and expand the signal, that expansion means from that 30 seconds of time, the signal is now 60 seconds of time. If it was f of 2t, we know that the signal here is going to compress, so instead of the signal being 30 seconds, the signal is now going to be 15 seconds. So our b factor here represents how much of a scale your time axis is going to be affected by. So what happens if we apply this to some sine wave here? And what's going to happen to the actual frequency of the signal? So we basically know that from our observation on the previous slide, if b is more than 1, the signal here is going to compress. And if b is less than 1, the signal is going to expand. So if we go back to our previous explanation, I'm going to write this here on the slide for you guys. Let's say we assign an arbitrary value for t here. So t was 30 seconds. We know that frequency here is basically going to be 1 divided by t. So when we go 0.5 of t here, f, this means our new time here, instead of being 30 seconds, is going to be 60 seconds. Because we know that basically for b less than 1, as we saw in our previous slide, the signal itself is going to expand. And then if we went f of 2t here, The time it actually takes here is going to be 15 seconds accordingly. So if we do the inverse of this to get all frequencies, just make sure I don't confuse people here because I'm using the functions. So if we obtain our frequency here for these, you can basically see, I'm going to use a calculator for this at this point. Right, so if we take 1 divided by 16 here, sorry, 1 divided by 60, this here basically, oops, sorry. This here basically is going to give us a frequency of 0.067 Hz. And this one here is going to give us a frequency of 0.0167. Right? So in our observation here, we basically know that when b is less than 1, because the signal expands, we end up occupying more time for one instance of our signal. That means we stretch out the actual time itself, and accordingly our frequency is affected. And then if our signal is compressed, meaning that if b is more than 1, we occupy less time. So as of such, when we occupy less time, we get a higher frequency accordingly as well. So for b less than 1, the frequency is going to be less in particular. Oh yes, my calculations actually are off. Whoops, sorry. Yes, they are. Right, so yes, the solutions are the other way around. My bad. Yes, my bad. So basically, for when you have b less than 1, as we saw on the previous slide, for b less than 1, the signal expands, and because the signal expands, that means we have a slower frequency. And for when b is more than 1, our signal compresses, so that as such, we have a higher frequency as well. So yes, we just basically need to swap the decimals here accordingly as of such. Here was my calculator. Right, so this one, oops. So this one is 0.167, and this one is going to be 0.067. Yes. Thank you for that correction. All right. So recapping, basically, if b is less than 1, we know basically our signal is going to expand, so that means we have a slower frequency. But when b is more than 1, our signal compresses, so we have a higher frequency as of such. Alright, so let's consider the following signal here for a discretized time signal, because we actually need to observe the effect on discretized time signals as well. So if we consider the following signal here of x of nt, okay, can't erase that. Alright, I'll fix the slides afterwards. So yeah, let's consider the following signal here, and we have x of nt here equal to the modulus of n. We know n here goes from -3 to 3, and common n here can only be represented as integers. And t here being equal to 1 second enforces this property. So from n -3 to +3, and because we have the modulus sign here, that means n of x of -3 will just be +3, +2, +1, 0, 1, 2, 3 accordingly, and so forth. So what this looks like is basically going to be a series of instantaneous values for each instance of n here accordingly. So for n equal to -3, the instantaneous value at this point here, because it's a discretized time value, is going to be 3. For n equal to -2 here, we have an instantaneous value here of 2. The -1 is going to be 1 here, 0, 1, 2, and 3. So the difference between a continuous time plot and a discretized time plot, the continuous time plot will give you like nice straight lines accordingly. But a discretized time plot is just going to be stems representing instantaneous time at which the sample was taken. So the overall time of the signal in discretized time is actually represented by the number of samples we actually have. So we know on n here went from -3 to +3. In compressing this, we're going to have to obtain what is going to be our new spacing, or referred to as a new time spacing here, to figure out how actually do we obtain this compression. So we knew that our original time interval, n is on the x-axis, sorry. So n here is actually on our x-axis. And answering the question, MATLAB does help with studying the signals, yes. But there's also a free version, well, I can't really say it's a free version of MATLAB, there's a freeware alternative to MATLAB, also known as Octave. So I'll type this in the chat here for you guys. The values represented on the y-axis here basically are the instantaneous values or the magnitudes that we captured. So basically what we had, go back one slide. Where we had x of nt here equal to modulus of n. When we plot here for n -3 and t equal 1 second, that means this is going to be -3 by 1 here. We had x of -3. For the modulus here of -3 will give us a value of +3. And so forth for -2 will give us +2. -1 will give us +1. 0 will give us 0. 1 will give us 1, 2, and 3 accordingly. So this here represents the magnitudes that we obtain from the actual equation of x of nt. n, even though it says time in seconds, is actually supposed to be n here. So here is going to be what we had, n of minus equal to minus 3. So when n was minus 3 and our t here was equal to 1 second, which is our constant for discretized time, that means that x of negative 3 is going to be giving us a magnitude of 3 here, because x of nt was equal to modulus of n. And yes, and rightly pointed out in the chat, n is not a unit. N represents the sample number. So remember here, x of nt was equal to modulus of n. And we knew that t here equal to 1. N went from minus 3 to 3. So if we watch here for when n was equal to minus 3, and we know t is equal to 1 second, minus 3 by 1 here is going to give us x of minus 3. N here being minus 3 is also going to substitute in here. And because it's a modulus, that means we only could take the positive value of it, or the magnitude, so we get positive 3. And as such, our end result here is such that it's going to be x of minus 3 is just going to be 3. So that's how we obtain the magnitude of 3 here on our y-axis. And for our instance here of n equal to minus 3 is represented here on our x-axis. Similarly, for our instance where n is equal to minus 2, when we plug in that minus 2 here into our x of nt equation, we're going to obtain a magnitude value here of our resultant is going to be positive 2. So n here represents our sample number. So from minus 3, minus 2, minus 1, and so forth. And thus it is plotted on the x-axis. Y here is mapped as the resultant of the entire equation. So does that help with your question? Right, so that's what I'm getting at. So when we did our new time space in here, or our new n space in accordingly. So remember, in this case, so we can basically say, if we want to compress this to occupy half the time, we can say half the space. So what's our new spacing? So remember, t here is basically the time between n samples. And n here would be basically our instance. So for this particular instance, this is actually how we compress our signal by manipulating n instead of t. Because for a discretized signal, t is actually constant. So yes, t is actually the set time given between samples. And we represent the sample instance on the x-axis being n. So, some people in chat already answered the question. So what's it going to be our new spacing? So our new spacing here is basically going to be 0.5. And in particular, this is because we, instead of occupying from -3 to +3, we wanted to make sure that this compresses by half. Yes, the actual sample number is changing instead of the time between the samples. Yes. And as a result, the time changes accordingly because we're now compressing it with respect to t. Oops, nope, I'm saying that wrong. Yes. The sample number remains the same, sorry. But our sampling time changes with respect to compression. So let's observe this for a particular instance here. We now know that our time spacing here on compressing the signal is going to be t on 2. We knew that our original time for our signal here was 1. But because it's t on 2 now, that's 0.5. N still goes from -3 to +3. So let's watch for n equals to -3 here for a new time spacing, right? So x of 0.5 of t, sorry, I'm doing this wrong. I need to do this in order to make sure nobody gets confused. So we're going to substitute in n equals to -3 here, and we're also going to substitute in t equals to 1 for a mathematical equation. So we have x of -3 multiplied by 0.5 multiplied by 1. And this entire thing here is going to resolve into x of -1.5. And then because we know this is going to be modulus of n, so the modulus of -1.5 is just going to be 1.5. So in compressing our signal, we basically affect the sampling time. So yes, that -3 to +3 basically tells you how many samples you are taking. And in this case, because it goes from -3, -2, -1, 0, 1, 2, and 3, that actually is, as if you counted it, 7 samples. The compression here is actually when you start manipulating the sampling time or the spacing in between two successive samples. So in compressing this, instead of being at t equal 1 second, we now go at t equals to 0.5 seconds. The x-axis on this graph here is actually n as well. So yes, it's a typical mistake I made when I actually put up these graphs. I'll correct them as I'm going. The question here is why not -1 to +5? Yes, it's because of where the 0 falls. And mathematically as well, when you watch x of nt, it also gives you the indication of where the actual samples lie and so forth. N is still -3 to 3, yes. But remember, we're doing this with respect to x of nt. And in this case, we had x of n 0.5 t. So remember, when we actually plugged this into our equation here, n is still -3, but now we have 0.5 here mapping, and t was 1 second. So our resultant here I'll just rewrite it. Would have been x of -1.5. And that's how you get the -1.5 that's represented here in this bracket on the x-axis here accordingly. Even though that our original n here was -3. So recapping, even though we put n here equal to -3, because this is a function of x, and we have 0.5 here and t accordingly, when we do out the multiplication here in the brackets, our end result inside the brackets here is going to be -1.5. I'm actually getting to that in particular, because if it's going to be x equal to -1.5, this value here actually is not going to be 3. As I showed here mathematically, this value is going to be 1.5. Which brings us to the point in time scaling discretized time signals. It's not always going to be a compression in the x-axis. It's also going to affect the y-axis value here accordingly as well. So this is actually the first stage in watching what happens when we time scale. Because the first instance we observe is that, okay, instead of it being of x of -3, because of the equation in the brackets here, it's not going to be x of -1.5. So we shrink by half in our x-axis. But as a result, because we have modulus of n here, because this is going to be x of -1.5, And that because we're going to have this value here accordingly, that means we also shrink this value here to be negative 1.5 accordingly as well. So yes, the x-axis is really nt and not just n. In some cases we just put n, but yes, in reality it is nt. For the sake of argument, let's say if we just kept this as modulus of n here, that means whatever value of n we had here, if n was a negative 3, this is just going to be modulus of negative 3 here, so that's how we obtain this positive 3 here accordingly. Any particular reason why for what? Can you elaborate? Alright, well eventually when I get the elaboration I'll go on, but I'm moving on to the next slide in the meantime. Alright, so in compressing a discretized time signal, that means when b here, which is going to be our multiplication factor, b is going to be more than 1, that means our time here is going to be t divided by b accordingly. And it's basically the opposite of what we observed for our continuous time signal case. Now, for homework, what I'm asking here is what happens if we actually expanded the signal by a factor of 2, what actually would happen? So backtracking by one slide. Alright, and answering the questions here in particularly. So yes, nt will actually be proper for the x-axis in these particular cases, yes, for the explanation. So you can actually say that these here will be nt. In particular here, I'm erasing this just to make a different point. Remember, this here is still modulus of n, and n here was minus 3. So that's how we still get that value of positive 3 here accordingly. But in this case, inside the brackets, it's going to be x of negative 1.5. So yes, the modulus or the magnitude is on the y-axis, and the result of what is in the brackets, being the square brackets, is the value on the x-axis. Yes, that's true. And yes, the value plotted on the x-axis is what is going to be the expression in the square brackets. Alright, so for homework, what I'd like you guys to do is to take that same discretized time signal and expand it by a factor of 2 instead. And what you'll observe is that instead of it going from n being from -3 to +3, it should go from -6 to +6 accordingly. Now, I'm going to give you an instance where, depending on what you have represented on the right-hand side of the equation, it may not only affect the time scaling, it may actually affect the amplitude scaling as well. So if we watch our signal here, in this particular case, we can see the signal here is not only a function of n, but it also is a function of t here accordingly as well. So if we put in n from -3 to +3 and t equal 2, and we plot it, we basically are going to get these values here, and if we stem plot it, we get this nice representation of our signal. Keeping in mind that n went from -3 to +3 in intervals, basically in integer intervals, and t here was 2 seconds. However, let's say we change the factor of t to be 0.5t. Because we have on our right hand side of the equation here, we included t. This means the amplitudes here change accordingly as well. So in our previous example that we saw, there was x of nt equal to modulus of n. So modulus of n was on the right hand side alone. We didn't have any t value. But in this example, we have n here, but we also have t. So depending on how t is affected on the right hand side here, this also affects the amplitude or the magnitude of the entire x of nt signal accordingly. And if we plot it, we basically see it also shrinks by a time factor of 2, but it's also amplitude scale because of that t value on the right hand side of the equation. So be very careful when you're doing time scale with respect to discretized time signals. Because even though that we saw in our previous case where t is equal to 2, and we went from n -3 to +3, we had these values here. So we had 0.95 here and 0.95 here on the beginning and end. Because the equation on the right hand side is represented by t and n, that means when you time scale, so instead of having normal t here, we go 0.5t. The amplitudes here also changes because of that t factor and the n factor here incorporated with it accordingly. So some applications why you actually may want to scale the amplitude and time would be that you actually, let's say if a signal is saturated and probably too slow or too fast. So I'll go back to my example with an audio signal. Let's say the hearing level of the audio signal is so high that it's deafening, and the signal is being played too fast or too slow for you to understand what's being said. You can actually apply these two transforms in one accordingly with N and T, so that way you can compress or expand your signal accordingly, and you can also affect the magnitude as well. So you can actually lower the volume level and slow down or speed up the audio signal in one equation. So you do this in particular when you want to make sure you do everything in one operation instead of two separate operations. Alright, so in time scaling of discretized signals, this only works when the signal value or the amplitude is not going to be a function of time. So we have a question is, what if we wanted to leave the amplitude as it is, but compress or expand the signal and the signal had a t term independent of n like the one in the previous slide? In that particular case, once there's a t term on the right hand side of the equation, the amplitude will always be affected no matter what. So you would want to do that in two stages of operations. So you'll want to time scale, yes, knowing that the amplitude will also scale accordingly, but afterwards you can just multiply the results by a certain factor to get back to the original values accordingly. So once there's a t term on the right hand side of the equation, you will time scale and amplitude scale accordingly. That cannot be helped. If it's just a function of n, meaning if there's only n on the right hand side of the equation, you can scale accordingly no matter what, and the amplitudes will not change. Anything else I would need to clarify regards to time scaling of discretized time signals? Yes, we will get examples to practice, especially in the problem sets. So by the time we hit the problem sets, I'll explain it in more detail for you guys to understand. Yes, especially for the time scaling. Yes, common N represents the sampling number, capital T represents the sampling interval. I'll fix the slides accordingly and I'll make sure that the axis shows NT instead of time, seconds, and so forth, and I'll re-upload the slides and so forth. Alright. Our next property is going to be time reversal. And this actually is pretty simple. This is basically, for any continuous time signal, you just replace t with negative t. And for discretized signals, you replace n with negative n. And instead of the signal playing forwards, or going from left to right, the signal now goes from right to left, or backwards accordingly. And later on, time reversal plays an important part in the topic that we'll be observing, known as convolution. But for now, we're just going to observe visually what happens when we do this mathematical manipulation for time reversal. So if I draw a line here representing a mirror, we can basically see that our original signals here are represented on the left hand side. But if we replace our x value here with minus x, we can basically see this is just a reflection accordingly to this mirror line. So instead of it going this way, it's now in a reflection accordingly, with this part of the signal is now on the left hand side, and this part of the signal here is on the right hand side. Similarly, for a discretized time signal, instead of it going from this way, from a low value to a high value linearly, it now goes from a high value to a low value linearly, basically just being a reflection here accordingly. So in short, time reversal is that whatever was on the left hand side of the signal now becomes on the right hand side of the signal, and so forth for the right hand side of the signal becoming the left hand side of the signal, and so forth. It's basically just horizontal reflection. The last property that we're going to observe here is known as time shifting. So, for time shifting, with respect to continuous time signals, the time shift is represented by tau. And in particular, if tau is positive, this actually lags or delays our signal. And if tau is negative, it advances or leads our signal. And the time shifting property is also important for convolution, which we'll also go into further detail when we reach that particular lecture. So let's actually watch some physical examples here of time shifting. So we have our signal here being x of t being tan inverse of t minus 1. Or we have our graphical map here accordingly for what it looks like. If we decide to shift this entire signal by -1, you can see here that this signal, being our original signal here, is shifted by 1 unit to the right. And this -1 here indicates this 1 unit shift to the right, indicating that our signal now is delayed by this 1 unit. Let's say if we wanted to shift our signal to the left instead. In that case, instead of it being t minus 1, the end result here is going to be t of minus 0.5. So this comes like if we just add 0.5 to our original signal. As of such, instead of the intercept here being at 1, our signal shifts accordingly by 0.5 to the left. And because of this positive 0.5 here, this is referred to as a left shift or a time advance of our signal. So, for negative values of shifting, the signal will shift to the right hand side. For positive values of shifting, the signal will shift to the left-hand side. The discretized time signals is just going to be a shift of n minus m. And the same properties holds true for continuous time signals. If m is positive, it's going to be a delay. If n is negative, it's going to be an advance. So as we can see here in our examples, we have n here representing the original signal. And in this case, because we have a shift of -1, we shift by one value to the right-hand side. In this particular case, because we have a shift here of +2, we shift by 2 values to our left-hand side accordingly. So recapping, once the shift is negative, we shift to the right-hand side. The shift is positive, we shift to our left-hand side. Alright, so are there any questions regarding time shifting? Okay, so apparently there are no questions on time shifting, so we're moving on to the next slide. If there are any... Oh, okay, we got a question. An example for the 2 dots to the right of the example are not in the front after the time reversal. Yes, this is actually an error here, accordingly. This dot actually is supposed to be on the left-hand side. So thank you for pointing that out. See if I can fix that one time. That's not supposed to be there. Right. No, that actually is correct. So the fix is actually shown here on the slide though. Thanks for pointing that out. In that particular instance, it won't matter, but let's say if the signal did continue, yes, it will matter at that point in time. So I'm just doing that just for illustration purposes to make sure everything looks symmetrical. And yes, it basically is a mirror image when you time reverse. For example 6, with the time shifting, then it's basically like shifting the vertical origin axis by however much left or right. Yes, it's basically is that. You basically just shift the signal left or right accordingly by the amount of delay. And if it's a negative value, in case of -1, you shift to the right by 1 unit. If it's a positive value, in the case of +2, you shift to the left by 2 units accordingly and so forth. So yes, it's basically like shifting the vertical origin axis. Alright, so we watched those three particular operations independently of each other. But in particular, when you're doing these operations, they tend to combine with each other for any questions or any particular application. So in applying these operations, the sequence in which you apply these operations are actually quite important. Because if the sequence is wrong, you end up getting a totally different output signal. So let's consider our g of t signal here and how we actually get to our a g of t signal accordingly. So what we observe here is that we start with our g of t signal and then we amplitude scale here, so we go a g of t. We then time scale, so we go AGT divided by B. And then the last instance is where we time shift to get our resultant signal. This is going to be AGT of minus T naught all divided by B. So the order of operations, which I'll recap on the next slide, is basically we amplitude scale first, we then time scale, and then we time shift. However, if we did the order operations in a different form, so let's say we start off with our amplitude scale here, but let's say we time shifted first. When it's time to time scale, what happens here is that only our t value here is affected by that time scale. The time shift here is not affected by this time scale mathematically. Now, it can be easily corrected in this example by just making sure that the time shift is also affected by this time scale. But for bigger and more complex equations, it's not so easily rectified. So the order of operations is always important for when you're actually doing signal manipulation. And yes, it is a property of math. It also will be a property when these signals here are no longer just at the power of 1. When you start going off into quadratics and cubic equations, the scaling factor here changes dramatically. So it is quite important to pay attention to the order of operations. This is essentially like BODMAS with respect to shifting and scaling. I'm going to give you the order of operations on the next slide. So when you're actually performing the order of operations, always perform this order as listed here. Always start with the magnitude scale first, then time scale, and if applicable, time reverse, and then the final operation will always be time shift. And yes, because t naught is a constant and t is a variable, and t naught is not affected by t. So always perform the operations in this particular order, you know, to do your signal manipulation. So make sure you always magnitude scale first, then time scale. If applicable, then you time reverse, and the final operation will always be time shifted. Alright, so that brings us to the end of lecture 2. In short recapping, we basically watched our 3 time properties that we'll be using for signal manipulation, which is going to be time scaling, time reversal, and time shifting. We also observed in particular that the order of operations is important for doing our signal manipulation, and order operations are listed here accordingly. You are allowed to skip operations once they are not applicable, but always perform the operations in this order. I will fix the slides with the discretized time graphs and so forth accordingly to rectify the explanations, and I will post them back up on myELearning accordingly and as such once I fix those slides. I also need to upload the introduction lecture with the fixes as well and so forth. So any fixes that I encounter while I go through these slides, I'll also make sure that they're finalized and I'll post up the corrected slides accordingly and so forth. Alright, so that brings us to the end of lecture 2. Are there any questions that need to be rectified at this point in time? Yeah, sure, I can go over time reverse. So, time reversal is basically where we, instead of the signal moving forward in time, the signal operates backwards in time. So instead of being positive t, we represent it as negative t, and for discretized signals, because we deal with n, instead of it being positive n, it's just going to be negative n. Visually, what that means is that it's just going to be a reflection of the signal. So we basically watch how the signal is here, we put a mirror line, and we just basically draw the reflection of it accordingly on the next side. So as we can see here, that our signal started with a constant value here on the left hand side and then decayed towards some infinite value. We just basically reflect the signal here accordingly to get time reversal. So this part here, which was on the right hand side of the signal, is now going to be on the left hand side of the signal. And this part here, which is on the left hand side of the signal, is now going to be on the right hand side of the signal here accordingly. So it's just basically a mirror reflection of the signal. The same holds true for the discretized time signals as such. It's just basically to reflect the signal accordingly. That's all there is to time reversal. Yes, it is considered equal magnitude, but just opposite in direction. I will have to check on the reverse signal being e to the power minus x plus 2. If it is, I will correct it on the slide. Put a note on the slide to make sure I check. Ah, okay, so someone answered the question to me. Thanks. Alright, any further questions? Alright, so let's move on to our last lecture for today. Annotation. Alright, so our last lecture for today is going to be special signals that we will be encountering throughout the entire course, and how these signals actually help us with manipulating and observing certain effects when we do signal manipulation. So throughout the entire degree, you will always see these four signals reoccurring no matter what. And these four signals are going to be the unit step, the ramp, the sinusoid, and the impulse. And we'll be looking at each one of these in turn throughout this lecture. So let's start with the unit step. The unit step is defined as u of t, where it is 0 for all instants of time before 0, and it's going to be 1 at time equals 0 and all positive values of time. Graphically, it looks like this. Basically, it's just where we have 0 from everything before time equals 0, and for everything after time equals 0 and at time equals 0, it's going to be 1. This signal is encountered, and particularly when you just basically switch on the circuit, or if you switch on anything. It's basically just an instantaneous value from 0 to some immediate value. So what happens if we multiply, say, any arbitrary continuous time signal here by the unit step? Basically, what that means is that everything on the left-hand side of t less than 0 means the signal no longer exists. And everything at t equals 0 and onwards means that the signal would exist for that point in time. Because the magnitude here is 1, that means we just get a perfect extraction of the signal from t equals 0 and then for all positive values of t. Yes, this would be an ideal unit step. We're talking about this in mathematical terms, not in ideal terms, because yes, it's basically just going to be a slope with a really steep gradient. But mathematically, for our explanations, it's an instantaneous change. Is a unit step signal like the clock signal from the FPGA boards. It is similar to it, but because you're dealing with real world components, it tends to be literally a very, very sharp ramp with a very high gradient factor. Because with real world electronics, there's a time for that change to actually occur. It's not instantaneous, but it gets very close to it, so to say. So the unit step basically always starts at time equals 0 and continues onwards for all positive values of time. The unit step never returns to 0. It is 0 before time equals 0, and at time equals 0, and for all positive values of time, it is going to be 1. It will never return to 0. If the previous question meant just for the rising edge of the clock or when the clock now turns on, yes. It's basically, that's going to be unit step. But mathematically, it never returns to 0. It's just a sharp change from 0 to 1, and it remains at 1 for all positive values of time. So the unit step is also referred to as a causal signal. And basically, any causal signal means it does not exist before t equals 0. Yeah, it's not a sinusoidal signal like the FPGA clock. It's just one instance of the clock, where the clock goes from 0 to whatever maximum value there is. Just only that one instance. So, reiterating, a causal signal is a signal that exists only from t equals 0 and then for all positive values of t. For t less than 0, the signal does not exist. This is a causal signal. It is possible to manipulate the unit step, as we saw from our previous signal operations in the last lecture. We can actually time shift the unit step accordingly. We can also time delay the unit step, and we can also time scale the unit step as well. But in particular, what we look at will be the time delays and the time reversal. So, at this time delay here, because we know that the time at which it switches on is t1, and we know the signal is shifted towards the right, that means t1 here needs to be mapped as minus t1 inside our brackets for a unit step. If we wanted to flip this entire signal, that means we just put a negative sign on the outside here only for all the terms. That means t now becomes negative t, and negative t1 now becomes positive t1. As such, we flip the signal accordingly to get this representation of it. And this is like if we just did the time reversal of the signal. In discretized time, the unit step is just represented in terms of n, with similar behavior to that of the continuous time unit step. But remember, because this is discretized time, we're dealing with samples, so for all samples before 0, it's just going to be 0. For all samples at 0 and onwards, it's just going to be a magnitude of 1. The next signal we're going to be looking at here is the unit ramp. And the unit ramp basically is, for all instance of time before 0, it's going to be 0. For time equals 0, and for all positive values of time, it's just going to be a positive gradient slope here, represented by the equation t. In this particular case, because we reverse the shift function, this does not go against all operations, because we basically flip the entire signal itself. So I'll go back to explain why. Let's say if this actually was so we know this signal here is going to be u of t minus t1, right? But let's say we map this as u of, let's say for some instance, u of x. This here is just basically u of minus x. Yes, this was along the y-axis. The flip was necessarily along the y-axis. Oh, okay. No, I see where you're getting confused. Okay. I'll actually re-explain it. So the order of operations is that we understand that this here is just going to be a time shift, right? So we understand that u of t would have been from this point here, and then t minus t1 means we shifted towards the right. So let's see what happens when we do the order of operations here accordingly to get what you're referring to. So if we did u of minus t, it comes like we just did like this. Instead of like this, it comes like we flipped the entire signal. So this now becomes like that accordingly. And then we want to get u of minus t plus t1. So that means we need to observe what happens when we have this instantaneous change here accordingly. So in this case, we know that our change occurred here when t is equal to t1. So if we actually said that this part here, t equals to t1, that means u of t1 minus t1 equal to u of 0. So that's how we know where our change actually occurs. Because u of 0 represents this vertical change here. Now, we want to go u of minus t plus t1. But we want to make sure what's going to be the value in this bracket here to get of u of 0. So that means that we need to say this part here, minus t plus t1 is equal to 0. Because we want that to resolve to 0 to get our vertical change. And what that means is that t must equal to t1 when we do our equation manipulation. And as a result, because we want that change, and we already reversed our signal, that means we have to have this change here at t1. So yes, the blue one underwent a reversal, then a shift. So because we know here that t must equal to t1 for this bracket value here to resolve to 0, and we also know that we had our u of minus t here being our reverse signal, which was what, +1 and then 0 otherwise. That means that for T1, we need to make sure that this shift here, this vertical shift, get back the laser pointer, this vertical shift here must be represented at T equal to T of 1. So that's why we get this vertical shift transition here accordingly. With both starting from U of T. Remember, the U of 0 point here represents this vertical change. Okay. Yeah, just say it. Feel free to ask questions. I'll go back and answer whatever we need to answer once I finish discussing the current slide. Alright, so we were on the unit ramp. Or the ramp signal in this case. Right. So a ramp signal is represented that for time before 0, it's 0. And then for time more than 0, it's just going to be T. Alright, what are you confused about? Okay, I see what you're confused about. Right, so one thing to note is that when we did those shifts in our previous lecture, T was positive. So the sign in front of T was positive. So if you added T to, if you added T1, to T, in that particular case, you would have gotten a shift to the left because the sign in front of T was positive. So we knew that, get back here, that if we went U of T plus T1, this would have meant that T1 here would have been on the axis. Or we would have went this way. Because we knew that from our previous lecture, once we had a positive shift being T plus T1, it would shift to the left. But however, in this case, the sign in front of T is negative. Once that sign is negative, that means the directions of shifting are going to be the opposite. So in this case, because the sign of T here is negative, when we go positive T1, the shift goes to the right instead. If the sign of T here is positive, and we have positive T1 here, so positive T plus T1, we shift to the left. But if it's negative T and then plus T1, we shift to the right accordingly. Depending on the sign of T, that will determine the direction of shifting. And yes, a good idea is to equate what's in the brackets to 0 to get the true x-intercept. Alright. So, the unit ramp here is basically an integral of the unit step. Which is basically like if we had a straight horizontal line and we integrated it. So if we integrated the value of 1, we have gotten the integral result being t. And that would just be our unit ramp here accordingly as well. And in particular, for physical circuits, you encounter unit ramp using something referred to as an integrator circuit. Yes, the formula calls for t to be positive for context, so once you make t positive, you'll get the shift direction accordingly. The discretized form of the unit ramp is basically... Why is this here? I do not know why this is here. Hold on. My ink annotations, I was here. 3. Right, save that. Right. The discretized form of the unit ramp is basically the same thing as the continuous time form, is just with respect to n, where everything of n before 0 is just going to be 0, everything at n equals 0 and onwards is just going to be n. Right. The sinusoid signal is basically defined as x of t equals to a cosine of omega t plus phi. A here is going to represent the magnitude, omega being 2 pi f will give us an idea of what the frequency is, and phi here represents our phase shift. This signal is basically encountered in many different forms of applications. In particular, it will be a repeating clock cycle form that you will be seeing. And the sinusoid always repeats itself at every 2 pi f cycles. We will encounter the sinusoid in particular when we start doing Fourier series and Fourier transform in later lectures. Thankfully, we will not encounter the discretized version of the sinusoid for this course. We will be only focusing on the continuous time version. So let's consider a different signal here referred to as our rectangular pulse. So the mathematical equation for the rectangular pulse is given by this form here, where basically for the time period between a on 2 and negative a on 2, we can represent this as being a modulus form, and we can say the magnitude of this is 1 on a, and then for everything else outside this time period, we just say that it's going to be 0. So the question is that we have this rectangular pulse, but what is the area under the rectangular pulse? Now, simply put, you can just take the length by the breadth and you can get the area, but mathematically this is basically going to be an integral operation. The reason for this integral operation excuse me. The reason for this integral operation is such that because when we start observing multiplications of signals with respect to the rectangular pulse here, we actually need to map this mathematically using an integral form here. So if we had some arbitrary signal, g of t, being multiplied by a rectangular signal here, p of t, the area under the product is going to be this integral form here in order to evaluate the actual area. As of such, if we needed to get the area underneath this curve here for a rectangular signal, the mathematical formula for this is actually our integral form here. multiplication of the two signals will basically be that where we have the extraction of the signal here accordingly, and it will be magnitude shifted by 1 on A. So we can rewrite the area formula into this form here accordingly, because we know that for a rectangular signal, the magnitude here is just going to be 1 on A throughout the entire time period. And then we can evaluate the integral here accordingly by using a first principle operation, where we can say the limit as A tends towards 0. And because of the upper and lower limits of the integration approach the same value, being 0 in this case, that means the integral part, and because of this g of t property being continuous and finite at t equals 0, that means the value there is going to approach g of 0. So as of such, if we do all the mathematical operations here accordingly, we evaluate the limit here and the integral, that means because we approach g of 0, we can extract this out. And as of such, the limit as A tends towards 0, when we evaluate this, we'll get g of 0 of limit A tends towards 0 of 1 on A multiplied by A when we substitute in these limits here. And this limit factor here will just cancel out, and we obtain g of 0 here. So the reason why this is like this, why it is like that, is because when you do an integral, remember, the integral for when you're crossing 0 is done in 2 steps. And as of such, you're doing it such that you do the integral from negative a of 2 to 0, and then you also do the integral from 0 to a on 2. And upper and lower limits of that integration will approach the same value, being 0. So when you mathematically evaluate the integration here, you're basically saying that you need to do this integration in 2 steps, because you cannot cross 0 doing an integration operation in mathematics, because then you end up getting the wrong value. So you need to break this integration to encounter that 0 value. So as of such, it will go negative a on 2, 0, of g of tau, d tau. And then you need to do another integration, a on 2, 0, of g tau, d tau. It's the same operation for the rectangular pulse. When you do the same integral, you still have to break it up accordingly for both sides. You can't cross the 0 value doing the integration for mathematics. And because they approach that 0 value, being they approach 0 here, and they also approach 0 here, this being the upper limit. And this here is the lower limit. At that point in time, on your axis, that is going to be g of 0. So because of the limit evaluation, you will get g of 0 accordingly, because you're going at a tends towards 0. So that's how you extract out g of 0. Alright, so at that point in time, when you do all the maths behind it, and you do the limit evaluations, and you extract out the g of naught here, and you evaluate this limit with the integral, you realize that the limits here basically cancel out, and you just get g of naught. So as the a value tends towards 0, the rectangular property here, the rectangular pulse, has the property of extracting the value of any continuous finite function at time equals 0. And this property holds true because once you integrate between any limits, including time equals 0. This property is what we refer to as the sifting property. And we'll encounter this later on in more details when we hit sampling and convolution in particular. So as a tends towards 0, and we obtain this g of naught value here accordingly, the rectangular pulse is now defined by delta of t. And delta of t is what we refer to as our unit impulse. Mathematically, delta of t defined as equal to 0, and we basically say time not equal 0. And that the area under the unit impulse, if we integrate it accordingly to set limits, is going to be 1 for any real number where eta is more than 0. So what these mathematical terms mean is that basically the unit impulse has infinite height and 0 width, and the area under the unit impulse is always 1. But for all purposes, throughout the course, the unit impulse here will have a magnitude of 1. So as of such, because mathematically at t equals 0 it's not defined, we cannot evaluate this as a function. We just basically say it's the unit impulse. If we treat it with a magnitude of 1, and it's just an instantaneous value in time at that particular time. It is possible to shift the unit impulse accordingly, so we can say the unit impulse could go t minus t1 or t plus t1. And if we do the integral evaluation for this, we just basically extract out a particular value for that particular impulse. Was there any reason for the rectangular pulse having a magnitude in relation to its duration? Or was this just the example? This was just for the example. This is just to show for the example that once it is symmetrical about the y-axis, you can actually do this evaluation. And yes, once the magnitude is also related to the duration as well. So, in doing time shifting of the unit impulse, if we actually do an area evaluation of it across any arbitrary g of t or g of tau signal, the property observed here is that basically we can use the unit impulse to actually sample a particular value of any arbitrary signal, in this case or g of t or g of tau signal, and we can obtain the instantaneous value at that particular time. So in short, what this means here, and if I draw it out for you to explain this, it comes like we have some arbitrary value here, which is g of tau, and then we apply our impulse here accordingly, which is going to be delta of t minus t1. And to get this instantaneous value here, this is just going to be g t1. So the maths here accordingly with the unit impulse and time shifting it relates as to how we obtain this g of t1 value. And this also refers to the sifting property of the unit impulse as well. So if we try to evaluate the following here, where we integrate the unit impulse, and we know that the properties of the unit impulse is that the area is concentrated at t equals 0 and it's going to be 1. That means if we integrate the unit impulse with respect to t and negative infinity, we get a result of 1 for t more than or equal to 0, and a result of 0 for t less than 0. And this representation here should look very familiar. We actually saw this representation as a previous signal. So in particular, what happens here is that if we integrate the unit impulse, the result of the integration of the unit impulse will give us the unit step. And if we integrate the unit step, the result of that will give us the unit ramp. Right. The reason why we say unit is because unit impulse and unit ramp means that it tends to be a magnitude of 1. And that's all what the unit in front of it means. There's a magnitude of 1. And apologies, but in correction in this, if we integrate the unit step, we just get the ramp signal. Not the unit ramp, the ramp signal. So the integral of the unit impulse gives us the unit step. And the integral of the unit step gives us the ramp. Oh, okay. Right. Conversely, if we differentiate the ramp signal, we will get back our unit step. And if we differentiate our unit step, we'll get back our unit impulse. Alright, so that's the end of our 3 lectures at this point in time. In recapping this last lecture, we will be particularly using the unit impulse and the unit step throughout this course. We will rarely use the ramp signal, and we will encounter the sinusoid signal when we start doing the Fourier series and the Fourier transform. As we saw in the previous lecture, lecture 2, the unit impulse, the unit step, the ramp signal, and the sinusoid signal can be time shifted, time scaled, and time reversed accordingly. The operations that we saw can be applied to these signals as well. The order of operations also apply to these signals when you are manipulating them as of such. So are there any questions related to the content of lecture 3 at this point in time? So answering that question, sinusoid and convolution means you only have to do one instance of convolution. And I believe the problem set should have an example of this, so you can actually see how to do it. But it is a little bit difficult because you need to know what properties to look on the trigonometric table to reduce the equation correctly. But if once it's in the problem set, and I believe it is, I will actually show you which properties on the trigonometric table to observe when doing that convolution. The A basically represents any constant value in particular. It just basically means that, okay, A could be 2, 3, 4, 5, 6, any positive value. That's all it represents. Non-integer as well. It can be anything from any decimal value, so long as it is not negative. So it can be 0.1, 0.2, 0.0035, so long as it is a positive value. Alright, any further questions? Tau just represents the time shift. The tau is just like when we had t minus tau. Tau is just basically the value at which you time shift as. So if you went minus tau, it shifted to the right hand side. If you went positive tau, it shifted to the left hand side. Just any value you can think of to represent your time shift. Oh, if you're referring to tau here in our signal evolution in this particular lecture, tau is just a substitution for the integration. That's all it represents in these mathematical equations. But for the time shifting, it just represents any arbitrary value. Alright, so if there are no further questions, that brings us to the end of today's session. If anyone has any questions, please feel free to leave them in the comments down below, or you can email me privately with questions regarding this. I will fix the slides for all the questions and feedback that I got in today's lectures, and I will post the new slides accordingly up on myELearning with the correct fixes to rectify all the concerns and whatnot that we had, to clear up any confusion or any misunderstandings as of such. Because I am saving the annotations accordingly as I go along, and I will rewatch the videos to make sure in case I miss anything that requires some clarification. Our next session will be next week Monday at 4 PM accordingly, and I actually can't remember off the top of my head what topics we'll be focusing on at that point in time, but I will post up the lectures way beforehand on myELearning. But our scheduled time is next week Monday at 4 PM here. So until then, take care, be safe, and I'll see you guys soon.